All right, hello there. So today we're going to do section 4.2, and if you watch the video that I posted on the site from 3 Blue 1 Brown, I told you a little bit about, or showed you some pictures of like null spaces and column spaces and what are called kernels. And so let's learn about that today, how to find those. So grab your highlighter, and first we're just going to look at a null space. So a null space, it's written NUL with an A right there, so the matrix A is given to you, is a set of all solutions to this homogeneous equation, AX equals 0. So basically, to find the null space, it's very simple. You just augment your matrix with 0 right here, and you go ahead and RF it. And that would produce, in this case, 1, 2, 0, 13, 33, 0 there. Okay. And then the last one would produce, the next row would be 0, 0, 1, negative 6, and negative 15. All right, so you can see there, if you wrote our answers the old-fashioned way that we kind of used to, remember I have x1 here, x2, x3, x4, and x5. All right, x1 is going to be negative 2x2 minus 13, x4 minus 33, x5. X2 is free. X3 has quite a couple things in it, 6x4 plus 15x5. Then x4 is free. And also x5 is free. All right, now we could write this out. If you notice here, I have three things going on. I have some x2s, I have some x4s, and I have some x5s. So basically, if I wrote out this answer, I would have my answer for x1 all the way down to x5 would be, if I made it into like a vector format, it'd be a vector times x2 plus another vector times x4 plus another vector times x5. And so I don't want to write those there because this next little part has you write them out. So those vectors, those three vectors would be negative 2, the coefficients, negative 2, 1, and then 0, 0, 0. The second vector going with x4 would be negative 13, 0, 6, 1, and 0. And the other one going with x5 would be negative 33, 0, 15, 0, and 0. All right, oh, no, 0 and 1. All right. So you can see we have three vectors. So these are basically the spanning set of vectors for the null space. All right. So notice each vector is size R5. All right. There's 5 things, which matches the number of columns. But our null space, since it's not equal to the 0 vector, all right, then we know that our null space is automatically going to always have the same number of vectors in it, the same number of pieces in it that as you had free variables. Okay, so there's 3 free variables in this answer, or in this problem, and that means we have 3 vectors, right, in the span of the null space. Okay, all right, so that's just a little tidbit. All right, so now we talk about column space. So column space, the definition is very simple. Column space is written like this, and it's just all the set of all the linear combinations of the columns of A. So literally when somebody gives you the columns of a matrix, that's the column space. So it would be like taking these things right here and a linear combination of those columns, that's the column space. So to see if something is in the column space, you basically just see if it can be made by those vectors. So, you know, you want to see, like, I'm going to do this one down here. If W is in the column space, if this is in the column space of that, I just want to know, is A times some random thing, can it ever come out to W? Okay, so what you do is you take A, augment it with W, and see if it has an answer. All right, so in this case, when you do that, so if you take 5, 21, 19, 13, 23, 2, and 8, 14, 1, augment it with 5, negative 3, and 2, and you get your RF, and you get 1, 0, negative 2.5, 0. You get 0, 1, 1.5, 0, so everything's looking good. But here you get 0, 0, 0, 1. So that was not good. So my answer to this question would be no. It's not in the column space of A. So W is not in the column space of A. All right. Now, to check and see if something's in the null space, it's really simple because remember the null space is all the things, all the ways to make 0. So if you want to check if something's in the null space, all you have to do is take your original matrix, multiply it by the item that you're using, and see if you get 0. So it's a little simpler. So you take your 5, 21, 19, 13, 23, 2, 8, 14, 1, and you multiply it by the matrix. So when you do that, it's a 3 by 3 and a 3 by 1, so you get a 3 by 1 for an answer. So if I just do the first row by hand, 5, 21, 19 times 5, negative 3, 2, so I get 25 minus 63 plus 38, and that comes out to 0. And so do the rest. So the answer to this is yes. W is in the null space. Okay. All right, so here are just some little facts about the null space and the column space and how they compare. So the column space of a matrix is a subspace of Rk. So Rk, K being the number of rows. And in this case, in this vector right here, there are 4 rows. All right. The null space is a subspace of Rk, but this time K is the number of columns. And remember, the number of columns is the number of variables of something. So in this case, there are 3. Okay. So letter C says find a non-zero vector in the column space. So remember, that's just a simple thing to do. Something in the column space is just a linear combination of the columns of your matrix. So here's a 3 columns like laid out, and all I have to do is pick a non-zero vector and multiply it out to multiply by these things, and then that vector is in the column space because it's a multiple of our original vectors. So it said to do non-zero, so I'm just going to do an easier one and make this 3, but make the other one 0 so they don't really do anything. So the first vector times 3 just turns into 3, 6, 9, and 0. So this right here is a linear combination, a linear combination of the columns of A. And notice its size. It is 4 things. It's a member of R4. It's 4 dimensions. All right. So here, this one says find a non-zero vector in the null space. So we've taken that vector and augmented it with 0, and then over here, given the answers. So if you look at this answer, you got x3 is 0. So that's coming from right here. Then x2 is free. That's coming from this guy here, because no pivot there. And then I got x1 is negative 2x2. So that's right there. So x3 is 0. So that's going to be here. It says x2, so x2 is free, so I'm going to pick it to be 5. And then x1 is just supposed to be negative 2 times whatever x2 was, so that one was going to be negative 10. All right, and notice that this is in the space R3. So anything that's in the null space is size 3 right there, so it's 3 dimensions right there. Okay, so that was just kind of show you that. All right, these little rules right here, are these little contrasting things between the null space and the column space are just little things you can read through. The only thing you might not recognize is, remember this is the columns, these are the rows, because remember matrices go m by n, like alphabetical order, the rows and the columns. All right, implicit and explicit. Explicit means you're like just given the thing. Implicit means you have to find it. Okay, so explicit is like, you know, when somebody gives you the column space, the matrix, that's the column space. The null space you have to find yourself because you have to like solve your AX equals 0. You have to like do your augmentation and solve it and all that kind of thing. All right, this next little bit, remember just from before that if you want to prove something is a vector space or a subspace, you have to do these 3 things. Have the 0 vector, addition works, and scalar multiplication works. And then you also have these 3 theorems here. If you have vectors they're in a vector space V, and the span of those vectors, then the span of those vectors is a subspace of V, all right? So basically it's telling you that if you basically like segment a part of your vectors out of your vector space, if you take a part of them, then they're also a vector space themselves. So you can like break it up in different little ways, right? The null space of a matrix is a subspace of Rn, which you already knew, and the column space is a subspace of Rm, okay? All right, so in this next little piece right here, we're gonna try to show if these things are vector space. We're going to try to say like what size they're as, basically like by these rules that were given to us before, right? So first of all, we have to show that it's a vector space to begin with. And so this one right here, I have x and y, and this has to be true. X minus y has to be 4. So if I try to make the 0 vector, so if I try to say, okay, let's let x be 0, I can't make y be 0 because x minus 4 has to be 0. So if x is 0, that means y has to be negative 4. And I can't get the 0 vector. So 0 vector is a no. So this one is not even a vector space itself. So why bother? All right, this next little piece right here, if we try to do on letter C, if we try to do some things to just kind of show that it's a vector space, first of all, I have to just go ahead and try first thing, 0 vector. So there's nothing stopping me from making x, y, and z all 0, so that's a yes. Second thing, does addition work? So if I make up a vector, 2 vectors and add them together, do I get a third vector that looks like this also? So let's try it. So let's see, let's make up a vector where x equals 2 and y equals 1. So if I do that and I plug it into this piece right here, I would get the vector 3, then I would get 1 and 3 if I do those little formulas. All right, so let's make another one of this time x equals 4 and y equals 2. So if I do that, I get 6, 2, 6. 4 plus 2 is 6. 2 times 4 is 8, 8 minus 3 times 2 is 6 is 2. So that's what I'm doing here. So add these together. So add those together, I get 9, 3, and 9. So if this was a vector, and it was supposed to follow these rules right here, 3y would have to equal 9. So 3y equals 9, that means that y is 3. So in that case, then up here, x plus y, this has to equal x plus y. Well, I already know that y is 3, so x would have to be 6. All right, so let's check out the middle one to see if it worked. Well, 2 times x minus 3 times y, so 2 times 6 minus 3 times 3, so 12 minus 9 is 3, and that's exactly what it was. So yes, this thing does also follow that. So the last one would be to prove with multiplication, like scalar multiplication. And that would work too, so I could prove it to you just this way, but for time-wise, we just won't do it. All right, so this one is a vector space. So what you can say right here, S is, if you want to break it up, you can do it like this. S is the vector 1, 2, 0 times x plus 1, negative 3, 3 times y. So S is basically the span, or all the linear combinations of V1 and V2. All right? So S is a subspace, with a C, of R3, because there's 3 rows to these matrices right here. So it's a vector space, okay? And that's by theorem 3 from the last page. All right, this next one here, letter B. So again, if we tried to kind of prove it like we did letter C, everything would work out here. And I can do the 0 vector. I can make x, y, and z all be 0, and that's fine. So 0 vector works. All right, and then if we kind of look at what's going on right here, I have x minus y equals 0, and then I have the next one, y plus z equals 0. So what I have right there, if I'm trying to see what's going on here, I have 1, negative 1, 0, 0 right there, 0, 1, 1, 0. All right. So basically, this is saying there's one free variable. All right. So there will be one vector in the null space. Okay. So by theorem number 2, it's going to be a subspace. And it matches V, because V also has one vector in it. Okay? All right, so the next little part, the last little piece right here, kernel and range of a linear transformation. So a kernel is basically just another name for the null space, kind of the same thing, but a kernel is the null space of a transformation. So it's something that when you do a transformation on something, it makes 0. But remember, when you do a transformation on a matrix, it's just basically matrix multiplication. Okay, so kernel and null space are pretty similar. It's just like a different name because you switch to a transformation, but it's basically pretty similar. All right, so we're just going to do one little example on that, and then some little review at the end, and that'll be it. All right, so this example is for the kernel, and so this is my transformation. I have something that transforms something with 4 dimensions down to 2 dimensions. So if you take a vector like this, the transformation is that you're supposed to do this to it, and it's supposed to equal 0, 0. All right, so let's look at what's going on right here. So basically what I'd be telling you, if I took something like this, 4, 2, 5, and 1, if I took and x plus y is supposed to be 0, and z plus w is supposed to be 0, so I can't use that. Let me erase those. So if I did this, that'd be like 2, negative 2, and 5, negative 5. So it transforms it down to 2 dimensions. You're supposed to add x and y, so 2 plus negative 2, and 5 plus negative 5, and obviously those come out to 0, 0. So it says, what form do all the vectors in their kernel look like? All right, and so I gave you an example right there. It basically takes it down to 2 dimensions, and if you look at your problems right here, if you look at these equations, I got x plus y equals 0, and I have z plus w equals 0. So we're going to go in this order, x, y, z, then w. I know it's not alphabetical, but this is how it looks. So I have basically x, I'm sorry, I was going to write the matrix. So I have this matrix, 1 for x, 1 for y, 0 for z, 0 for w, has to equal 0. 0x, 0y, 1 for z, 1 for w, has to equal 0. So if I produce some answers right here, this one right here, I have 2 free variables. So remember, this is x, y, z, and w. So x would have to equal negative y, which we already kind of knew from my example over here. Y would equal itself. Z would have to equal negative w, which we kind of already saw right here. And w has to equal w. So if I go ahead and list like we did on the very first example, my vectors there, there are 2 vectors, one in terms of y, one in terms of w. So I have negative 1, 1, 0, 0 for the y vector. And then the one with the w's, I'd have 0, 0, negative 1, and 1. So these 2 vectors would be my kernel, K-E-R-L, all right? So these vectors, the span of these vectors are in the span of the kernel. All right, so just to finish up right here, this last example here, remember that I'm not going to do these, but just to remind you, if something is to see if something's in the null space, what you do is you take your vector, you multiply it by the item that you're trying to test, and does it equal 0? And in this case, if you do these 2, yes, it does. All right, and it's something in the column space. Remember, that's a little bit harder. So you want to see if this is a linear combination of the columns of this matrix right here. And so you have to test it out. You have to do A with augmented with W, and you have to see if is there a solution. Now remember, it can be infinite solutions or one solution. It just can't be no solution. And so in this case, if you do that with these two things up here, yes, it is. Because what happens is there's infinite solutions. And it works. So the answer to both of these is yes.